welcome once again. It's Physical Sciences Extra. My name is Tinyiko Kosa, and we are going to have again another hour and a few more minutes of a lesson. And today we're going to talk about electrodynamics. Now, what is this all about? We will hear as the lesson proceeds. So we're talking electrodynamics today. This word here, electro, sort of suggests what we're going to talk about. We're going to talk about things that has to do with electricity and other things as well. Now, the focus of the lesson, right? The focus of our lesson, we're going to be talking about magnetic field. We will know what a magnetic field is, and we will also look at permanent magnet, what we use them for, and we'll also have a look at magnetic field around a current carrying conductor. Okay, so there would be some magnetic field due to a current carrying conductor, and we will also talk about current carrying conductors in a magnetic field. So this time we take current carrying conductors, we place them in magnetic field and try to see what happens. And under here, we will be looking at something called Fleming's left-hand rule. Okay, so when we put conductors in current carrying conductors, when we put them in magnetic field, we need Fleming's left-hand rule to help us understand some movement that those conductors would have. And that leads us to a section called motors, where we talk of electric motors. Here, we will also look at electromagnetic induction. So there is an induction, something is being induced to something. And when we talk about some electricity, let me just mention that, induced, we can't do that without talking about generators, electricity generators. And we will also talk about alternating current, okay? And in here, we will bring in something called root mean square values. And we'll also talk about, of course, the direct current, DC. Okay, so that will be the focus of today's lesson. Let's just start and begin to talk about magnetic field. Perhaps the first point to start on is to ask ourselves, what is a magnetic field? Okay, so what is a magnetic field? A magnetic field, so let's try and define it here. A magnetic field would be a region or space around a magnet. Color changed. Let me go back to my color. All right. Around a magnet where another magnet or a magnetic, so that's or a magnetic object or magnetic object will experience a force. Okay? So that will be a magnetic field. Now, if we have a magnet, we would have a magnetic field existing around that magnet. Now, if I have a magnet, I know a magnet would have the north and the south pole. So say here I've got this magnet. Say this represents a magnet. And this is the north, and this is the south pole of the magnet. Now, this magnet will create a magnetic field around itself. And the direction of the magnetic field is from north to south. So direction of magnetic field is north to south. So in this case, it means I would have magnetic field lines to represent this, going in this fashion, okay. I would have magnetic field lines like that, like that, like that, can have few more. And the direction is from north to south, that way. So north to south. And why are they in this fashion is because north will attract south. So if I have, instead of one bar magnet like that with north and south, if I have a magnet, say with north here, okay, another piece of magnet there, south. It means I'll have magnetic field going in that direction. Okay? So that is what is going to happen. Now, the magnetic field around this magnets will be detected, or we will know there is a magnetic field existing if we bring another magnet or a magnetic object, okay, like a piece of nail, magnetic objects. So these will help us to see if we've got a magnet around, and we will know that when this magnetic object experiences a force. Now, this part here, talking about the direction of the magnetic field, I've already explained that. I said the direction of the magnetic field is from north to south. So direction of magnetic field is from north to south. And of course, we use field lines to represent the magnetic field like I've shown earlier on. So it's from north to south. We've got the south pole and the north pole of a magnet. Right. Now, magnetic field around current carrying conductors. This suggests to us that when we have a conductor that is carrying current, there is current flowing in it, that conductor, without any existence of a magnet around it, it will create a magnetic field around itself. So any current carrying conductor creates a magnetic field around itself. Now I want to try and show how this would happen. Say I have a conductor, all right? A conductor that is carrying current. Try and draw this nicely here. So if I've got a current in a conductor, and in this case, I look at the cross-sectional area. So by cross-sectional area, what do I mean? If this piece of pen represents a conductor and there is current flowing inside it, if I cut here, I've got a cross-section of the conductor. If I look at this point here, what I will see is only that cross-section. I won't see the rest of the conductor. So if I have this conductor here, looking at it at that point, and say in this case it is carrying current into this page, we make use of this notation here to say the current is going into the page. Okay, so we use a cross for that. We use a cross for that, into the page, a cross like that. And this cross, let me just put a circle around it to show that it's a cross-section of a conductor. Now, when I have a cross like that to represent current carrying conductor carrying current into the page, what we use to show the magnetic field created by the current carrying conductor around itself, we make use of the right-hand rule, okay? And the right-hand rule is such that we're saying, let the thumb represent the direction of the current. And if the thumb represents the direction of the current, our curled fingers will represent the orientation of the magnetic field around that conductor. So it will be telling us the direction. So if this current here is flowing from this point to that point, my thumb should point in the direction of the current. And my curled fingers show the created magnetic field around that current carrying conductor. So in this case, if it is into the page, you will agree with me that the curled fingers will be in a clockwise direction. So in this case, if I then have to indicate the magnetic field around this one, I would have circles like that with the direction in the clockwise direction. The direction of the field is that way. So it is curling in that way. But then if we have a current carried out of the page, okay? Current carried out of the page. So this conductor this time is like that, again, cross section, but the current is coming towards me, okay? So out of the page. Out of the page, we make use of a dot to illustrate that, okay? We make use of a dot to illustrate that. So a dot like that will say the current is coming out of the page, okay? So remember, I always have the circle to represent my cross-section of the conductor. Now, what will be the direction of the magnetic field? Now, this current now, it's coming towards me. It's out of the page. So if it's out of the page, my thumb in the direction of the current, there's the page. Out of the page, the curled fingers are in the anti-clockwise direction, and therefore my field lines will be, of course, circles around it, but anti-clockwise direction. Okay, so that is what is going to happen in terms of the magnetic fields created by these conductors. But quickly, I want us to get back here. And this is the reason why I left this space here unused. Say instead of looking at the cross-section, we look at we just look at an area of the conductor in this way. So we look at, we say, okay, this conductor is, let's just look at maybe 1 meter of the conductor or 50 meters, whatever the case may be. So say that is the conductor. Okay. So that's the piece of the conductor that we have concentrated on. The conductor may be long, but we are just looking at that point. And let's say we have the current this time. Let's say we have the current this time. Let me use this color for the current. Let me use green. Let's say the current is going or is in that direction there. Okay? Let's say the current is in that direction. So let me try and put it somewhere right in the middle. Pen is failing me. Yeah, there we go. So that is the direction of the current. Okay? Now, in the same way, now just look carefully on the screen there. I'm going to use my thumb here to show the direction of current in the conductor. So that's the direction of the current. My curled fingers tells me the direction of the magnetic field. Now, you would see that on the left side of the conductor, okay? Look at it carefully. This left side here, my curled fingers are like coming to me, so it's out of the page. But for them to curl like that, it means on the right-hand side, they went into the page and curled out of the page from the left. So from the left, I'm seeing them coming out of the page. And what is the notation that we use for out of the page? We're using dots to show that, okay? So we're going to use the dots that out of the page, this is what we have. So this side, we've got out of the page. Pardon me if it doesn't come out nicely. Trying so hard to use this pen. Okay, there we go. So this will be the magnetic field around this. Okay, and I'm going to now show you, deliberately increase the space between this thing, and perhaps also using just dots, okay, like that. On the right hand side, okay, wonder if I should use a different pen here, different color pen. On the right hand side, you would remember that my fingers are going into the page. So into the page, I've got X's. So X, 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 X. Okay, so I'll have the X, 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 X. I'll have the X's there. Watch the space getting bigger as you move further. Okay, from the conductor. There we go. There we go. There we go. There we go. Now, that should be an X. All right. So what is this showing us? You would see in the first place that as you move further away from the conductor, the strength of the magnetic field becomes less. Strength of magnetic field decreases as you move further away. In both sides, if you look at this side, if we check the distance between the dots, you could see that it is increasing as you move further away from the conductor. And that tells us that the magnetic field strength is decreasing as you move away from the conductor. So that will be into the page and out of the page. And for one piece of conductor, we're taking a length of a conductor here. We're taking a length, L, of a conductor. Okay, so here, the same way, I mean, even if we had this I'll just illustrate it differently. Even if we had the conductor in a horizontal position here, this piece of conductor in a horizontal position here, and we had the current moving, say, in that direction, all right? In the same way, watch the screen. I've got my thumb in the direction of current. My curled fingers give me the direction of the magnetic field. So it will be coming out of the top side, and it will be going in from the bottom side. So going in from the bottom side, I would be seeing X's here. Coming out of the top side, I'll be seeing my dots there to represent that. Okay, so that is all here that we need to look at in terms of finding the direction of the magnetic field. Okay, so in terms of, if you want to join this, because this field lines, it means here you've got a line that goes in here and comes out there, goes in here, comes out there, goes in here, comes out there, goes in here, comes out there. Okay, in that way. So that's what you are having. So you've got, remember this is three-dimensional, so you've got lines all around that current carrying conductor, giving you the magnetic field around it. So that is how you find the direction of the magnetic field. Current into page, current out of the page. That's how we do it. Now, let's look at something called Fleming's left-hand rule or left-hand motor rule. Now, when we have just, or our definition of the magnetic field suggests that something that is brought into a magnetic field will experience a force. If something experiences a force, we know that the result of a force could be movement. If that force is big enough to give you a resultant force acting on that object should start to move. So if this force experienced by a magnetic object or a magnet itself is such that it can make it to move, it means we should be able to know how that is going to move. If it is placed in a magnetic field for which we know the direction, and we also know perhaps the direction of the current, or we don't know. But the fact that if that particular object is in there, it's going to experience a force, it is ultimately going to move. Now, the Fleming's left-hand rule helps us to find out the direction in which such an object is going to move. Let's look at it briefly. The thumb of your left-hand rule here will be representing a force. So that part here is the force. In other words, the lift, the pushing or the pulling that particular object is going to experience. If it is a conductor placed in a magnetic field, we will need to know the direction of that magnetic field so that we can tell where the current is going if we know the force. In the same way, if we know the magnetic field and we know the current, the direction of the current, we can also tell in the direction of the force or the direction in which the object is going to move, because we will know the direction that the force is going to take when it acts on that particular object. So this rule is very important. You must remember it all the time. Your thumb, it's your force. Your first finger, it's your field. And your third finger, it's your current. Okay, direction of the current. Now, can we apply then this rule to answer some of the question? Let's look at example 1. Example 1 here says, determine the direction in which the conductor will move in the diagram. Okay, so we're looking at the conductor and tell in which direction it's going to move. For us to be able to do that, we should be knowing the other things. The red tells us that this is the current. Okay, so current is moving in the upward direction. And this is our conductor here. The black piece inside here is the conductor. But what do we know about the magnets? These are permanent magnets. Okay, so these are placed in there. They are permanent magnet. We place them in there, and then we bring in the conductor. Now, north and south. We know that magnetic field direction is from north to south. Okay, so that is the field, the magnetic field. And upwards is the direction of current. Okay, that's upward for the current. Now, how are we going to tell? Fleming's left-hand rule helps us to find the direction of the force, or if the direction of the force is given to us, we can also use it to find the direction of either the current or the magnetic field, depending on which ones are given to us. We need to be given two to know the third one. Now, it has to be the left hand. Now, I must start by knowing which hand is my left. Is it this one or this one? Now, I think this is my left hand. Now, so I'm going to use the left hand to try and find the direction of the force here, where the conductor is going to move when placed in this magnet. So now let's apply it. You see now, this is the direction of the magnetic field. This is the force, I don't know. This is the direction of the magnetic field, and I seem to have gotten it right. It's from left to right, north to south. There is my north and south. This one is the direction of the current. Oh yeah, it's not in the right direction. So I need to tilt my hand such that this one is still pointing in the direction of the magnetic field, and this one should now be pointing in the direction of the current, which is upward on my screen here. So I must be tilting it that way. You can't see the thumb now because it's pointing into the screen, and this one is pointing in the direction of the current, which is the red arrow here upwards, and that one in the magnetic field. So this means that the force that this conductor is going to experience will be such that it will be pushing it or pulling it into the screen as you see it. So the conductor, how this conductor is going to move, is going to move into the page here. So it's going to move inwards in that way. Now, there could be a better way, or not necessarily better, another way, an alternative way of finding it. We also call it the slap rule, this one. If you have your right hand, your fingers stretched in the direction of the field and your thumb in the direction of the current, if you were to slap or give a clap to whatever you're facing, that movement of your hand will be showing the movement in which the force is going to pull your conductor. So the conductor here is going to move inwards. So if I were to slap this, will be in that way. Okay? We will continue to be using both methods as we move on. Let's look at number B. In number B, you would see that we are having a cross-section of the conductor. We don't have a piece of length of the conductor, but a cross-section. So we have cut it and just look at where we have cut the conductor. And remember that the dot and that circle tells us that the current is coming out of the page. So in this case, it is coming out of the screen. So it's coming out of the screen. Now, another thing that we know is that magnetic field is from north to south. So let's draw it. So this is this way, north to south. That's the magnetic field, north to south. Okay? Now we should try and make sure that the distance between these lines are equal. Why? Because the magnetic field inside here is constant or is uniform. All right? Now, if I were to use Fleming's left-hand rule, remember that this represents the force, which I don't know. I need to know in which direction that conductor is going to move. This represents the direction of the magnetic field, and this one the direction of the current. Now, the direction of the magnetic field is this way. So I need to, this will be quite tough for me to do with the left-hand side, and I mean with the left hand. So maybe the slap rule will be quick here, but I must show you how to do it using the left hand. So this must be pointing this way. This one is correctly orientated as it is. It must be pointing outside towards me, out of the screen. So how am I going to do that? I must tilt it in this way. So how is the conductor going to move? You can see that the force, which is the thumb, is pointing downwards. So the conductor here is going to move in the downward direction. We'll see the conductor moving this way. Okay. Now, the slap rule, there we go. This must be pointing in the direction of the field. This must be pointing in the direction of the current. So if I have this direction of the field, this direction of the current is out of the page, so I must have it that way. And if it is in that way, the slap will give me the direction of the force, which is the direction in which the conductor is going to move. It means the conductor is going to move downwards. So that's how you can actually find the direction that a conductor in a magnetic field is going to take. If it starts moving, it will move in the direction in which it experiences that force. It can, here we found that the direction or the force that that acts on the conductor is such that the conductor will be moving inwards. This one, the conductor is going to move downwards. So that is how we find the directions. Okay. Now, let's move on and let's look at another example. It says, determine the direction of the magnetic field and the current if you require the conductor to move to the left. Okay. So you want the conductor to move to the left, all right? Now, if you want the conductor to move to the left, there is only one way. If you want it to move this way, there's only one way that we can have this magnetic, the direction of the magnetic field and the direction of the current. So it is moving to the left. Let's apply Fleming's left-hand rule. The left-hand rule says this must be the direction of the force, the thrust, that must be the direction of the field, and this must be the direction of the current. So if I orientate my hand such that this points in the direction of the force given to me, the red, so that's the force, this is the direction of the current, that will give me the direction of the magnetic field. So I have the two now when I have used my Fleming's left-hand rule in that way. This one being the force. So that's how I want the conductor to move to the left. This has given me the direction of the magnetic field. So the direction of the magnetic field will be from bottom upwards. Okay? In that way. That will be the field. But then what other thing am I given here? This finger here, all right? This second finger of mine gives me the direction of the current. So the current is coming out of the page. And when the current comes out of the page, what do we know? What is the notation that we use? We make use of a dot to say the current is moving out of the page. Okay? So that's how we can determine the direction there. The question was saying going to the left, but I've added something here. Say if we want this conductor to go to the right. Okay, what are we going to do, or how are we going to make sure that we get the conductor to go to the right? Because we need to do something about the magnetic field inside here and also the direction of the current. Now, Fleming's left-hand rule again. This must be the force, that must be the magnetic field, this must be the current. Okay? And then if that is the force, okay, this is the force, direction of the magnetic field, the current. What is happening here? The current is coming out of the page, but I have changed the direction of the magnetic field in that way. Okay? So how are we going to show that? The current is going, we can have the current still coming out, like you saw, but then changing the magnetic field from top to bottom will change the direction of the force from left to right. Okay, and remember that by finding the direction of the magnetic field, we have actually found the type of magnets, the poles that we're using here. If the direction of the magnetic field is bottom upwards, it will mean that what we have at the bottom is north, what we have up there is south. Okay? In the same way here, if it is from top to bottom, this will mean that this pole here is the north and that is your south. Okay? So that's it. That will be your how to find the directions there. You can use your slap rule as well. Let's look at it. Going back to the top one, if you have these fingers here in the direction of the field and this in the direction of current, and when you slap this conductor, it must go to the left because we want it to go to the left. So that is the force. It means that's the direction of the magnetic field, and this is the direction of the current coming out of the page. Now let's look at the second one using the slap rule, if it allows us to do so. Remember what is given to us? It's only this here. Okay, so if you have this is the, as you slapping it that way, all right? Slapping it that way, you understand? So you're slapping it this way. So when you slap it that way, it means you've got a force pushing it that way, and when you the fingers are pointing downwards, so your magnetic field goes downward. But then when you are slapping it this way, where is the direction of your thumb? Outwards, out of the page, so that's the direction of the current. Okay, so that's how we find the directions of both the magnetic field and the current if we know the direction of the force. Right, let's now start looking at something called a motor. And we'll be specifically talking about a DC electrical motor. The word DC simply stands for direct current. So here is a direct current motor. And if you look carefully here, you would see that we've got magnets. This one and that one. This one being the north pole of our magnet and the south pole. What do we know about magnetic field between a north and a south pole of magnet? The magnetic field will be from north to south. So that's what we're going to see. All right. Now, if we want our current carrying conductor, this blue here is a current carrying conductor, okay, inside the magnet. So this is a conductor, and it is carrying current, and therefore we call it a current carrying conductor. Now, what do we know about current carrying conductors placed in magnetic fields? Current carrying conductors placed in magnetic fields will experience a force. Okay, now the force is such that because this is one conductor, this is just one conductor, you will see that the current inside it will therefore be changing directions. Now, if we want this current carrying conductor to move, say, upwards on the left side, this side here moving upwards, and this side here downwards, what can we do? What we need to do, we will need to apply our Fleming's left-hand rule. It says we want the force to be pushing it upwards. This must be the magnetic field there, so it must be going that way. So if it is to go upwards, the direction of the magnetic field, direction of the current, it means we expect this current here to be coming outward. So we expect it to be going in from this side. So when that happens, it means this side, the force is pulling or pushing the left side of the conductor to go upwards. And in the same way, it means that force, let me just use some direction here, this force downwards, and this force, this side, upwards. So it will be turning in a clockwise direction. And when that happens, this is what we would have. In the starting position, here, it is there, current goes in there, current comes out this side. So there's opposing direction of current here. When that happens, we see the conductor moving in a clockwise direction. This part is now up there, and the blue part is now down there. So here the force has pushed the conductor downwards, and here the force has pushed the conductor upwards. That will be the direction of the force. Remember, these are directions of the current, okay, in there. So that's what we're seeing happening. Now, when it gets there at that point, you would see that the magnetic fields from north to south will be in that direction. This is the magnetic field inside there. So when the conductor is up here, okay, right up there, it has turned to that position there. you would see that we have a situation where the direction of the magnetic field is actually at right angle to the direction of the current, okay? At right angle to the direction of the current, right? So we're reaching that stage there where this conductor here experiences actually no force. And when it experiences no force, then the question is it going to continue? Yes, it continues from its own momentum. Remember that anything that is moving possesses momentum, and momentum carries it further. And when it is now at an angle, it begins to experience the force again. Now, experiencing the force again until it reaches a point where it is actually where the blue and the red has actually swapped positions. In other words, the directions of the current have swapped positions. Remember, we started with the blue on the right and the red on the left. Okay, so that will be our position 3, and that is how the conductor would have rotated or moved inside the magnetic field. Right. Now, moving on, we're going on with the DC electric motor, explaining how it works. Let's see here. Now, if you look at the motor from the top and just look at the conductor inside, you would have the conductor. Remember that the motor is something that that uses electrical energy or converts electrical energy into mechanical energy. So a motor, let me just write that definition here. We'll be referring to it again once more later on. A motor is an electrical device that converts electrical current or electrical energy into mechanical energy. Okay, so you need to have an input of electrical energy. In other words, this part here is connected to an energy source, which could be a battery, okay, energy source, which could be a battery, so that you inject current into this. And where this battery is connected to the motor, we have what we call split ring commutator. So split ring, because you've got this part here and there's nothing in here, and then you've got that part here. These brushes here, the brushes actually, this brush is a black, it's made of carbon. That is also made of carbon. The negative is negative because it's connected to the negative terminal of the battery. And the other part is positive because it's connected to the positive terminal of the battery. Okay? And the brushes are splitted. In other words, they're not connected all around. They are splitted. Hence, we call this a split ring commutator. And this is when we see it from the top. So that's the top view of a split ring commutator. Now, if we look at it from the front, it is in this way. This is the commutator, and you would see there are spaces here. Let me use a different color pen. You will see there's a space there. Sorry. Let me use this color here. You will see there's space here. that space and that space, okay, and this space here. So this is split, it's not like circular. So as this thing turns, it turns and it can get to a point where these brushes, okay, so let's look at the brushes, where these brushes come to a point, as the conductor turns, can come to a point where you have got that. Okay, so this space here has reached the points of the brushes. And in that way, at that point, there is no current into the conductor. And when there is no current into the conductor, it means that there is no force experienced by the conductor. And if there is no force experienced by the conductor, what happens at this point? At this point, it is the momentum, like I explained, it is the momentum of the moving conductor that keeps it going, okay, until it comes back, and the one what was in the negative, in the positive is now in the negative, and it continues to rotate in that way. Okay, so that's how the DC motor works. Now let's move on to something, some diagram, some picture that is animated, sort of showing us exactly what is happening there. Let's look at it. It's still a DC electric motor. We have our magnets. We have the conductor inside, current moving, okay? And it is turning in a clockwise direction, as the arrow shows you. This is the source, this is the battery or the cell, right? Now, as it turns, there is time when the brushes, this point here, look at it. There's time when the hollow part where there is nothing reaches that point, and therefore no current into the commutator. But this thing continues to move because of the momentum. And one cycle is connected, one other cycle is not connected. And that is how the current is varied there. You've got current at one point, no current on the other. Current at one point, no current on the other. And this diagram here, of course, is found from that particular website there. So you can access it if you have internet. Right, let's now have a look at example 3. Now example 3 says, show on the diagram below how you could get the coil to move in an anti-clockwise direction. Now anti-clockwise direction as shown by that arrow, the green arrow. If we want the coil to move in that way, remember the coil is what is inside the magnet, inside the magnetic field. If we want the coil to move in that way, it means we want this side of the coil to go down and we want that side of the coil to go up. That is the anti-clockwise direction. In other words, we need to have the direction of the current moving on the left-hand side such that the force experienced pushes the conductor downwards. But what we know from the magnets here is that the direction of the magnetic field is from left to right, north to south. So if we want the force there to be pushing downwards, so let's just look at the left-hand rule. If we want the force there to be pushing downwards, okay, here, what are we going to do? There is the direction of the magnetic field. If the current comes out, okay, it's coming out of the page, it will be pushed upwards. So obviously, we would want the direction of the current to be going inwards that side so that it can be pushed downwards. So in that way, we would want the current to be going in here. So this side, I would like current to be going in. Going in means I would have the what? The X there. Let me just have it more or less in the middle there. So in from this side. Okay? Let's check here. The magnetic field, remember, it's from north to south. So that still stands. So here, I want it to go up. I want the force to be pushing it upwards. But the magnetic field is still that way. So this side, I want the current to be coming out. So according to Fleming's left-hand rule, pushing upwards, magnetic field direction, current should be coming outwards. And what is coming outwards? Coming outwards is, we use an arrow there. I mean a dot there to say the current is coming outwards. Okay, so that's how I would do to make sure that this coil moves in an anti-clockwise direction. I would have the current going in from the left and coming out from the right. Okay, so in that way we have answered that question. What are we going to do here to make sure that the current is anti-clockwise? I mean the movement of the coil is anti-clockwise. Right, let's then move on to generators. Now, what is a generator? A generator, look at it. A generator is an electrical device. Electrical device that converts mechanical energy into electrical energy. Okay, so if you look at this definition here, this is exactly the opposite of motors. So if you have a motor will be an electrical device that converts electrical energy into mechanical energy. But the generator will convert mechanical energy into electrical energy. So that is the difference between the two, generators and motors. Now, if you look at this, the setup, more or less the same thing, but instead of you bringing in current here, instead of you bringing in potential difference in here in the form of battery, you don't do that. You actually use mechanical energy to turn this coil here, to turn this coil in there, so that when you turn it inside the magnetic field, you have what we call an induced EMF on the coil, induced EMF or induced current into the coil. When you move the coil within the magnetic field, you're going to get current induced onto that coil or onto that conductor. Okay. And when you look at a generator from top to bottom, we have what we call, instead of split ring, we have got slip ring. Now, what is the difference between slip ring and split rings? Look at this one. As slip rings are attached to the brushes throughout their movement. There is no time when the slip ring, the ring would have a hollow where the brush is not connected. So all the time the brushes are connected to the ring there. So that is the difference between the slip ring and the split ring. Now, if you look at it from the front, you would see that you have got a complete, what will I call it? It's not necessarily a circle, but a complete oval shape that tells you that this thing is connected throughout. It is not actually, doesn't have open spaces anywhere. There's no open space here. It is all connected throughout. So you've got a slip ring here. It doesn't come to a point where you have got this, where this part is open and that part is open. You have something that is completely cyclic there. It is complete. It is not broken. Okay, so that would be the slip ring. Now, if we have a generator is going to generate or create current. Like I said earlier on, how is that current created? When you move the coil inside a magnet, you're going to create, you're going to induce EMF into the coil. You're going to get current induced into the coil, okay? And that current then can be used for other things. Now, let's move on to how is this current generated. Okay, right, so now let's move on to looking at graphs of current versus time and potential difference versus time. And let me be specific here. We're talking about a generator that generates AC current or alternating current because we're talking slip ring commutators. Now, here, if this is graph of current versus time, it means here we'll be having current, and here it will be time. And of course, time in seconds, current in amperes. All right. What we see happening is that we would have a graph of sine like going that way, that we've got current surging, getting smaller to zero, getting into the negative in that way. Hence the name alternating current. The same way for potential difference, V in volts, and here time in seconds, we're going to have the same kind of thing. So this is called alternating current, AC, okay? And that is how it is generated. So this generator is generating alternating current because we've got slip rings there. It's current throughout. It is connected to the brushes throughout. There's no openings. But then let's quickly have a look at what happens when we look at an electrical generator, which is actually direct current generator. In this case here, it is actually having the slip ring commutator, and therefore there are times when the current is when there is no current, and so we should, but on the other side, current is connected or current is generated, and we see that the graph of current versus time will be such that it is in one direction, okay? So we see current generated in one direction. So you have got things like that, okay? So that will be the graph for a DC generator, direct current generator. In the same way, we would have the V, potential difference versus time graph drawn in the same way. Okay, so that's what we would have. And because we don't want current to be coming to our appliances in that way, we make use of certain things called rectifiers, and we'll rectify it in such a way that we have sort of a linear current or linear potential difference coming into our devices in that particular way. So we rectify this type of current. Okay. Now, let's move on, and we are now going to look at example 5. Write down the difference between a motor and a generator. One, doing this, you just define them actually. Okay, the first thing you say is that a motor is an electrical device. Motor is an electrical device, my pen is horrible, that converts electrical energy into mechanical energy. Okay, and remember that the other one, generator, is exactly the opposite. A generator converts, okay, so I'm not going to write the whole sentence here. Generator converts, so when it converts energy, it converts this time mechanical to electrical. Okay, so that is the difference between the two, the difference between a motor and a generator. The difference between a DC generator and an AC generator. Here with DC you have got split ring commutator. Okay? And with AC you have got what we call slip ring. Slip ring commutator. Okay, so that gives you the difference between them. The next question, how would you increase the induced EMF in a conductor rotating within a magnetic field? Okay, you can increase it by increasing the magnetic field strength. Magnetic field strength. You can also increase it by increasing the number of turnings or windings on your coil. Windings or turns on the coil. Okay, you can do this. What else can you do? You can increase the speed of rotation of the coil. So if you increase the speed at which the coil is rotating, okay, the speed of rotation of the coil. You can do this and then you'll increase the EMF developed by the generator. Okay, and how will you increase the speed of rotation of the motor? Okay, the speed of rotation of the motor, how can you increase that? You can increase it by increasing the strength of the magnet. The strength of the magnetic field. The strength of the magnetic field, okay? Strength of the magnetic field. That you will increase the speed of rotation of your motor. Okay, now quickly let's look at example 6. How would you increase the induced EMF in a conductor rotating in a magnetic field? Think here we have also answered this one. We spoke about increasing the magnetic field strength. Okay, we spoke about increasing the speed. We spoke about increasing the number of turns. Number of turns on the coil. Okay. Right, let's briefly, in closing this lesson, talk about alternating current. And when we talk alternating current, like I've shown there, we have got current that comes in a changing form. You've got going up, positive current coming in, negative current in that way. But the current that is carried and we are using in our homes is actually what we call the RMS values. Here we've got VRMS. RMS means root, or stand for root mean square. What we use at home are root mean squares. So if we are to get the maximum, so VRMS is the maximum given by the maximum voltage divided by the square root of 2. In the same way with current, if we are to get the current that we are using, which is in root mean squared, IRMS, will be given by R, or I maximum, divided by the square root of 2. Right? So this means we are not receiving the maximums. We're not receiving those values here in our homes. If we are told that the current we are using or the voltage we are receiving is 220 volts, the maximum voltage is not this one. It's something bigger than that. Okay, so that's how we find our root mean squares and maximum current or voltage. Right, let's now have a look at example 8, which is based on RMS values. In South Africa, voltage is delivered in our homes at 240 volts. Calculate the maximum voltage at which electricity is supplied at our homes. Now, we know from the previous formula that VRMS equals V maximum divided by the square root of 2. Now, here we are calculating for the maximum voltage, so V max. What is the RMS value? Is 240. So we substitute 240 for VRMS equals V max, what we're looking for, divided by the square root of 2. Now, what will that be? So V max, therefore, V max will be equal to the square root of 2 times 240. Now, what is the square root of 2 times 240? We can do this and say square root of 2 equals times 240. And what is the answer? It's 339.41 volts. So this is the maximum voltage that is supplied, but as it gets into our houses, what gets into our houses is the VRMS, the root mean squares. We get it at 240. That brings us to the end of today's lesson. I hope you enjoyed it. It is time for me to sign out. Tinyiko Kosa. Bye-bye.